Today it is truly a pleasure to introduce Maxim Olshanii, who is an example of one of my favorite things about ITAMP, namely the extended family. So Maxim was an ITAMP fellow some years ago. He is now a professor of physics at the University of Massachusetts, Boston. He's made extremely important contributions to the study of quantum many-body systems, integrable and non-integrable, thermal and additive equilibrium. As just one example, he's one of the originators of the generalized Gibbs ensemble, a state to which even integrable systems will equilibrate. So think of him as a sort of older brother to look up to. So the floor is yours.
Thank you. Right. So as you can see, the title is longer, and I've put everything I have in this talk because the next slide is going to be a diagram connecting different pieces, and let's see if you can right. And so as an overview, let me minimize this thing. So as an overview, so I'm connecting several things. So the general scheme is this. So there was an experiment in Jean Delebarre's group where they serendipitously discovered triangular two-dimensional breezes in a Gross-Pitaevskii equation. And so the mystery was that it only worked for triangle shapes. And the question that buzzed community for more than a year was, what is the question, the answer to which is a triangle? And so the answer to this question was given in this beautiful work by Shigao and Zhai. It took almost one year and a half, and they discovered a particular Fermi-Bose map that works only for, in a given space, that works only for simplexes, and that would be triangles in two dimensions, tetrahedron 3, and so on and so forth. And this is the thing, I don't know how people discover things like that. I mean, you don't, they probably just come to you. It's one of the things that come out of the blue. So one of the questions remaining, and even this question is not even resolved in the original Shigao paper, is how come? So this whole story is in fact not even Gross-Pitaevskii, but hydrodynamics. So what does hydrodynamics do with an infinitely sharp drop of the density in the initial conditions Jean Delebarre had? And even in numerical simulation in the Shigao Zhai paper is not hydrodynamics. It's still Gross-Pitaevskii. It's not clear how hydrodynamics survives it, and it's not clear if it lives forever. And this question is similar to the question, to the literally $1 million question of whether from any initial conditions you can propagate the Navier-Stokes equation forever, or there is a catastrophe that at which you would need to restart your conditions. And so we also I think serendipitously so we realized that the explanation for this phenomenon that hydrodynamics survives infinitely sharp drop in density and thus infinite forces lies in an old Chandrasekhar's paper from 1943. So gives a particular solution to the nonlinear transport equation. Then there's a map that from the nonlinear transport to hydrodynamics discovered by Bogdan Damski. There's another map discovered by Pitaevskii and Roche from untrapped to trapped particles, and with all that, we come here and we give an alternative explanation to the phenomenon Jean Delebarre observed, and there is a beautiful correspondence between our results and the results. And all these results over here now. So since I think I intrigued you sufficiently, so I'll start explaining what the phenomenon was. And so the phenomenon is published in PRX in 2019. So it's Jean Delebarre's group, and the PI on the project is Roger Saint-Jean. And so what do? So they in the beginning there's no trap. So there is a flat sheet, flat background, and with light they're able to build corrals of an arbitrary shape, so like fences of an arbitrary shape, and they can prepare Bose-Einstein condensate in the ground state of the shape. Again, the bottom is at the moment flat, and you can prepare in any initial shape, and in particular you can start from a shape of the square. They tried a pentagon, hexagon, many various shapes, and so you prepare the ground state like that, and then you release the walls of the corral, and at the same time you build a two-dimensional harmonic trap around it. So the square starts evolving. So that's the time. It becomes something less of a square, and then with time, after three periods, it, roughly speaking, thermalizes. So it at the very least it assumes a round shape, and it completely loses the memory of its initial shape. And the story repeats for all shapes, but for triangles. So triangles instead they breathe. So at a quarter of a period of a trap, the triangle condensate turns upside down. At a half of a period, it fully restores its original shape, and then for many periods, it continues breathing. And this is the motion Jean Delebarre observed. And as I said, the very interesting question is indeed, what is this question? The answer to which is a triangle. An explanation comes indeed in the I think in the ingenious paper by Shigao and Jai. That can be actually, so 90% of the story can be explained at the level of free fermions. So let's pose the following question. So imagine that I have free fermions, and I prepare an initial state for free fermions, which is a tensor product of two shapes. So tensor product of a particular shape in real space with a constant phase space density inside and zero phase space density outside, times some other shape in velocity space, also constant velocity distribution, zero outside, and as in this tensor product. So again, so the phase space density is either a constant, which is as you could guess, m over 2 pi h bar to the power d. So the maximal phase space density allowed for the Pauli exclusion principle, times the product of two theta functions. One is a theta function that fixes a shape in space, and another theta function that fixes space in velocity space. And we can time propagate it. I mean, you can time propagate it with Liouville's equation. But the question they posed is that, are there any circumstances under which the very same propagation could be obtained propagating the Euler's equation in hydrodynamics with some chemical potential, with some zero temperature equation of state? And this is a difficult question. And if somebody asked this question, posed this question to me 2 years ago, I would say no, because I mean, it's easy, of course. I mean, in the initial conditions, if everything is monotonic, it's easy to derive to link the force to the density and say this is my function, but it must be the same mu of n at all subsequent subsequent instances of time. Nonetheless, okay, well, let's try. Naive guess would be disks. So the naive answer would be, what if I start from the initial phase space density, which is a tensor product of two disks, one in real space, one in the velocity space. there's a knowing and somewhat ambiguous minus sign that floats here. So we would, in order to, for further consideration, we would need to flip upside. We would need to invert one of the two geometric figures. I mean, this is a small technical question, but what we get as a velocity distribution at a given point is not a disk anymore. So we get some kind of a lens type shape, and thus the relationship between the energy density at a given point and the density in the given point will depend on time, because initially it will be governed by the disk shape distribution of the velocities, and now it is given by the lens type distribution. And so the next question, which is a very natural question, is this. So imagine I have two shapes. Imagine I have a shape. I make two similar copies of the same shape. I can rescale one of them, and then I can do a parallel transport of one shape with respect to another. So what is the shape for which the intersection of two shapes homothetic to it is homothetic to the original shape? And if you think about it for a second, what you will realize is that the shape is a triangle. So again, as I said, we would need to flip upside down one of them. So this is two homothetic copies of the same triangle. And now what we realize is that when we intersect two triangles, and so what is this intersection again? This intersection is the local in space velocity distribution. Local in space velocity distribution remains an equilateral triangle. And thus, what emerges is a universal dependence of a local energy density on the density. And as you could guess from all the things, so scale invariance and two dimensions and so forth, the dependence is purely fermionic. So chemical potential is proportional to the density, as it should be for two-dimensional fermions. However, the prefactor is entirely new. So if you compare it with the standard equation of state for spinless fermions, you will get a 2 pi here instead of 4 pi square with 3 square root of 3 square root of 3. So what it constitutes is effectively it's a new equation of state. It's not an equation of state for a unitary gas. It's not a unitary equation of state for free fermions. It is a new fermionic equation of state. And now now one can reformulate the question. And the formulated question is, under what circumstances velocity distribution of zero temperature fermions remains self-similar at all times? And the answer is it needs to be a tensor product of simplexes. And then what is also important is that the further propagation must be happening in a harmonic trap, because only there these simplexes will be only rescaled and moved parallelly around, but not modified. And that this is precisely the setting for Jean Delebarre's experiment, except he has bosons. But now the very small move. So we just take the equation of state for this new fermions that we obtained, replace the Planck's constant by a fictitious Planck's constant, and then set the fictitious, because the thing doesn't care whether the Planck's constant is real or is just an upper bound for the phase space density artificially posed. And so choose the artificial Planck's constant in such a way that this combination becomes the coupling constant for the two-dimensional bosons, and so thus we get exactly the setting for the Jean Delebarre's experiment. And indeed, so if we solve hydrodynamical equations according to the scheme, we will reproduce Jean Delebarre's experiment completely. So one question that remains is indeed, so even though all this is hydrodynamics, in the initial conditions there will be an infinitely sharp jump in density, and thus infinite force, and it's not clear what hydrodynamics is going to do with it. One needs to find a way to regularize this sharp jump. And here comes the Chandrasekhar solution for the nonlinear transport equation. That was published in 1943 in a classified report. And this paper, in fact, is a derivative of a paper he published, or rather internally published 5 months prior. And the title for this paper is Optimal Height for the Bursting of a 105 millimeter shell. And the year is 1943. So the title is not an accident. And so the paper that followed was called on the decay on the plane shock waves. So there is a particular map from the nonlinear transport equation to the adiabatic hydrodynamics of gases that is not of interest for us at the moment. But what is important is that he looks at the nonlinear transport equation. So that's the simplest nonlinear equation, that nonlinear PDE that is interesting to study. What it describes is non-interacting particles on a line that moves with constant velocities. So each particle has a velocity u, but instead of treating them as with Newton's equations, we are interested in how the velocity depends on the coordinates and how this dependence changes with time. So this is what it describes. And as we could guess, if at any point the velocities of the particles behind are higher than the velocities of the particles in front, there will be a catastrophe. So the nonlinear transport equation will cease predicting anything, because we'll have, instead of one, we'll have 3 velocity classes at one point. The underlying Liouville's equation for the particles will still be working, but this is not what we're studying here. We're studying the actual nonlinear transport. So we get a catastrophe, and I cannot help it but to popularize my favorite popular book on catastrophe theory, written by a great British popularizer of mathematics, Jan Stewart. Never translated to English for some reason. He's written it directly in French. It's a beautiful comic book on catastrophe theory, and he recently edited the book that influenced many of us, by Courant and Robbins, on what is mathematics. And so many of the things many of us know about mathematics is from this book. It is written for high school students at the time in 1941. So right. And so catastrophe. And so what Chandrasekhar suggests for his problem is a particular exact solution for the nonlinear transport equation. This is extremely simple. So it is just 0 t. So it's but what it describes an approach to and dynamics after a catastrophe, but in particular after a catastrophe. So this is a dynamics after these particles all collided in one place, and then they, so what happens, how the thing smoothens it out. And it turns out that this catastrophe is precisely the initial condition Jean de Lebar has in his experiment. So we take this catastrophe solution, and then we move further to a map discovered by Bogdan Damski, and this is a map between the one-dimensional hydrodynamics and the nonlinear transport equation. So it turns out that if your initial condition is such that the density is proportional to the square of the velocity with a particular prefactor, so then the time dynamics of the hydrodynamical fields can be mapped exactly to the time dynamics of the nonlinear transport equation, and at all in the beginning and at all subsequent times. So you generate a class of a particular class of easy solutions of the hydrodynamical equations. And so, right. And then, so as we could see, all of that was in the absence of the trap. There is also in two-dimensional Bose gases. There's a map that owes its existence to a particular symmetry of the two-dimensional Bose gases. So it's in SO21 symmetry. It's a closed algebra of the moment of inertia generated with scaling transformations and energy. And thanks to this map, we can actually solve untrapped problems and then map them to the trapped ones. And I'll skip this part. And it turns out that we can, starting from the Damski-Chandrasekhar Shockwave through Damski's map, through Pitaevskii and Roche map, we can in fact connect the ends. And it turns out that the initial singularity we have in the hydrodynamical solution is nothing else but the very initial stage of the Chandrasekhar's Shockwave, again discovered in 1943. And here is a comparison between the hydrodynamical solution, which is as exact as it can be, that on the other hand matches experiment beautifully, and this is a solution that has nothing to do with the red line. So this is a solution that derives from the Chandrasekhar's Shockwave at later times. So it's not the very initial, so it's already smoothing. But the answer to the question of what regularizes the initial density jump, the answer is that Chandrasekhar's Shockwave. So what we're seeing is a Chandrasekhar's Shockwave. And this is plotted along the vertical axis of the three-dimensional gas. A big question remains: why Gross-Pitaevskii chooses this particular solution just after the jump? So there's a perfect match, but is it? I mean, how does it know? How does it know what to choose? And we don't know yet. I mean, one hint is if we can prove that Damski-Chandrasekhar Shockwave is unique in some sense, and if we can prove that there's no energy scales beyond the hydrodynamics in the game, so then this would prove in fact that Chandrasekhar's wave is what we need. So this part is easy. The scales are easy. So indeed, we can look at the energy scales beyond the hydrodynamics. So there are several. So we understand that in reality, I mean, so in Gross-Pitaevskii there will be also healing lengths. So there will be a region around the wall of the corral where the density is not exactly flat. So there will be some acceleration energy for particles on the slope, and it turns out that this particular energy is the factor healing length over the size of the system smaller than the hydrodynamical energy scales, which is chemical potential times the number of particles. There's a hydrodynamic uncertainty energy. So because there's some spatial dependence, that's some non-trivial contribution to the momentum distribution. Still of the same order. There is an energy scale associated with the fact that the wave function derivative is discontinuous, and it produces slow tails in the momentum distribution. Still the same scale, still psi over r, which is the small parameter, still healing lengths over the side of the system. So it turns out that indeed, I mean, sharp as it is, the beyond hydrodynamics effects don't produce energy scales higher than the hydrodynamical. And this analysis is similar to the one that happened in 1996 with a sharp derivative jump of the wave function on the edge of the Bose condensate when one passes from the Gross-Pitaevskii to Thomas Fermi. So there was also it wasn't also clear if the energy introduced by this cusp is smaller than the hydrodynamical scales, and it turns out that there it's even smaller. It's r square times a log. So so this is one out of two ways we need to prove in order to prove that this Chandrasekhar's wave is guaranteed in Gross-Pitaevskii. So from the point of view of Navier-Stokes equations and from point of view of existence, non-existence of solutions of ODEs, it's always interesting what controls what. So it's always the same story. So you have an approximate equation. Say, I don't know. Imagine you have imagine you have not even Navier-Stokes. So imagine that you have a hydrodynamics without viscosity, and hydrodynamics predicts a shock wave, and the shock wave you wouldn't know what to do, but if you introduce more exact terms, if you introduce viscosity and heat transfer, this would allow you to actually to get through the catastrophe, and this will allow you to predict with what initial conditions to restart your dynamics after the catastrophe. And this is similar to what is probably happening with Big Crunch and Big Bang. So if Big Crunch happens, we would really need to know the grand unification theory in order to restart our standard model after the Big Crunch and after the Big Bang that will happen, that will follow. And it turns out that we have two of those. I mean, two types. So we have the type of a catastrophe at the initial condition, so infinitely sharp jump in density with infinite forces, and we wouldn't know what to do with those. And we have another catastrophe over here where three shockwave fronts.
Yeah. Maxim, no question. So how did Jean Dalibard do these experiments to really create this sort of discontinuities?
So at the Gross-Pitaevskii level, there's no discontinuities. So it is
in the experiments.
In the experiment as well. I mean, so what his experiment modeling, what his experiment deals with is a Bose condensate. So the at the edge there's a Tanch smoothing of the jump in density. So Gross-Pitaevskii regularizes
numerical experiments. They were not.
Sorry.
These were numerical experiments, you mean?
Oh, he never simulated hydrodynamics.
Yes.
Yeah, he was always simulating Gross-Pitaevskii, and the authors of the explanation also. And so this is precisely the point, that everything is nicely hydrodynamical between the two catastrophes, but somebody needs to bring you through the catastrophe and tell you how to restart hydrodynamics after the catastrophe. And this is similar to the three-dimensional shock waves in gases as well. So if we don't know the velocity, if we don't know the viscosity, we wouldn't know how to connect the universe on one side of the shock wave and another side of the shock wave. So everybody before us was doing Gross-Pitaevskii that regularizes the singularities, but doesn't know how to connect the life before the singularity and after. And so the second singularity is indeed when three shock waves collide in the center. So in both cases, what happens? So in the case of this kind of singularity, what happens is that the shockwave front moves with some velocity, but then after the singularity, the velocity of the shockwave front abruptly changes its sign. And in this singularity, what happens is that there's a particular velocity field in the bulk, in the flat region, that shrinks from here to here, and this velocity field, after its reemergence, abruptly changes velocity. So it's like with flying saucers that can suddenly change the direction of their velocity. And right, and here the story, and here the Gross-Pitaevskii plays a role of the grand unification theory. So it is smooth. It knows how to regularize. But the interesting thing is that so our current understanding of why other shapes survive the catastrophes and don't survive the catastrophes, and triangles do. It's because at this point, at the point of this singularity, there's also another theory behind the hydrodynamics, which is this free-fermionic Liouville's equation, that for whom this point is not a singularity at all. And this is this theory that brings the solution from one end to another without introducing irreversibility. And so Gross-Pitaevskii simply follows. I mean, Gross-Pitaevskii also knows about this free fermions. But more to be done here. So this is our current understanding that what preserves this breathing is indeed the existence of the underlying fermions, underlying free fermions behind the two-dimensional interrupting bosons. Right, and this is so for the free fermions, as I said, there's no singularity at this point. So in summary, so we inserted our alternative explanation for the phenomenon observed in Jean Delabarre's experiment with triangular breathers, and so there's an explanation through the map to free fermions, and what we are inserting is an explanation that first of all that links this solution to a known solution of the nonlinear transport equation, but also brings us closer to understanding of how hydrodynamics coexists with initial and subsequent singularities in density. So open questions remain. So why indeed Gross-Pitaevskii decides to realize Damski-Chandrasekhar catastrophe and nothing else? I mean, after all, it could. We start from a tanch in front of a wall. I mean, it could decide to do something else, but it does precisely that. An interesting question is this: so the very same reasoning would apply to non-equilateral triangles. However, numerically, only equilateral triangles show breathing, and both are supported by both a Fermi map, and this is an entirely open question. We don't know what to how to answer it. There are also disc-shaped breathers observed in the same series of experiments, and there is a suspected quasi-revival and at the period 2/7 of the period of the trop. There's another suspected full revival at 2 periods of the trop. We're working with it, but this is a difficult. This question is much more difficult and convoluted. Support from various sources. So people involved. Doomsley Deschamps, so he's a master student in my group. Jordi Torrens from the University of Barcelona. Marina Gonchenko, she's actually a professional mathematician. Vanya Dunko, so UMass Boston, and Gregory Astroharchik, so Polytechnic University of Catalonia. And I want to conclude with my favorite quote from Michael Berry says nothing is ever discovered for the first time. And thank you very much.
Thank you.
Thank you for the talk. Does anybody have any questions?
So maybe I'll ask one. So how much the fact that you describe, the Gross-Pitaevskii equation sort of predicts, this, what is it called, the Damski-Chandrasekhar phenomenon is a manifestation of the fact that the Gross-Pitaevskii equation itself is an approximation. I mean, there's an inherent approximation that is made in order to derive the GP equation.
I mean, for the purposes of this work, Gross-Pitaevskii is the exact theory. I mean, it's the fact that, so Jean Delabarre didn't observe any beyond Gross-Pitaevskii effects, even though they should violate the scale invariance. They should violate the absence of the length scales in the two-dimensional Gross-Pitaevskii. So the next level of approximation is time-dependent Thomas Fermi. So or otherwise known as Madelung's map. So you work with the wave function square as a density. You work with the gradient of the phase of the wave function as velocity field. You neglect the contribution to the kinetic energy that comes from differentiating of the density profiles, and you arrive at hydrodynamics. And this hydrodynamics, it does show Chandrasekhar's shock waves. The question was that in the initial condition for the shock wave, initial condition for the shock wave is in fact singular, and it is not. So at the formal level, it does correspond to the initial condition for the Gross-Pitaevskii equation, but it's not. In short, you cannot start at t equals 0. You have to start at t equals plus epsilon, and you have to force the shape for the Chandrasekhar shock wave. You have to force the shape at which the density is a parabola, and parabola of codant, and the velocity is a linear function of a codant. If you don't force it, the time propagation remains uncertain, and so it's still an open question why Gross-Pitaevskii decides to realize the Chandrasekhar shock wave and nothing else. And so it's not. It's if you believe it does. So if you then I would say it's not contradictory, but it's not guaranteed. So it's so what's the analogy? Well, again, I mean, the universe we live on is probably not contradict. So if somebody solves the grand unification theory and shows that our universe is a legitimate solution of it, then I mean, there will be no contradiction, but one needs to show that it is our universe that realized and nothing else. I mean, so that's the thing. I'm not sure if I'm. I wanted to give some other analogy. It's say. So at this level, the Chandrasekhar shock wave is not a unique continuation of the initial condition for the Gross-Pitaevskii with the Tanch jump of the density. It needs to be proven that it is really what is realized, and it's amazing that such a simple thing is realized. I mean, you've seen. I mean, it's all polynomials.
But is there any indication of another possible solution? I mean, like apart from the Shockwave, that is maybe not realized?
No. There's there's no other candidates, and as I said, if one can prove that the Shockwave is a unique hydrodynamical solution that leads that if you propagate it backwards in time and arrive at t equals 0, it shows an sharp jump in the density, then this would prove that it is unique, because as I said, Gross-Pitaevskii doesn't show itself at the hydrodynamical level. There is no burst of energy that comes from the primordial Big Bang, but this uniqueness is also needs to be proven. So it's a good question. Right. This is, and so if you wrote about the disk breezers, so disk breezers are not supported by any of these maps. So it is, if anyone wants to has some spare time, so this is much more of a mystery. And at the moment we have a suspicion that it might be a numerological coincidence between several things, like a syzygy of coincidences, but one needs to work on it more.
Actually, I have just a clarification question about this Shigao-Shai idea. So, can you say again? So this is this triangular is indeed. I mean, if you come at it from basically nothing, like I do, that's really a huge surprise. So, but what did they actually show? So they just solved the transport equation and you moved it to the Gross-Pitaevskii, or what is
right? So what they've shown was this. So for this class of initial conditions for the Liouville's equation, or for the so for this class of initial conditions of the Liouville's equation, the local, if you stay at one point in space and look at the velocity distribution at this very point, the velocity distribution remains self-similar. You'll get the same shape. The shape may be rescaled, so it may broaden, but it is the same shape.
Yeah.
So since your velocity distribution always has the same shape, you can show that in that case, the kinetic energy density at this point is proportional to the density, to the particle density, with the same coefficient, just because of this similarity. I mean, we know that for disks, right? So the free-fermionic equation of state is always 2 pi, regardless on the 2 pi times density, regardless of the density, because we know that the velocity distribution is a disk and now it's not a disk, it's a triangle. And so
why, if this is this overlap, why doesn't it work for at least a certain orientation of squares?
Of spheres?
No, squares.
Of squares, because
you could have that if you have the right overlap, that's also self-similar, right?
Yeah, but you have to prove it. You have to prove it for all overlaps.
I see. Okay.
Yeah, because what happens? I mean, what are these overlaps? So you have the initial spatial distribution times initial velocity distribution. You just force the initial phase space density distribution to be tensor product of the two. And then on the harmonic dynamics, so the only thing that happens is that these things are rescaled and they're moved around in a parallel transport. But they move around in all various fashions, and in particular, yeah, this thing will happen.
And for triangles that works, I have to think about that.
For
I believe you.
Yeah, no, for triangles of any shape.
Yeah.
Try it at home. So this shape, this blue shape, is homothetic to the first two, and this answers this question of what is this question, the answer to which is a triangle.
Yeah.
And I think you can prove that there's no any other shapes. So and they also have a suggestion in their paper. They also have a suggestion for unitary gases and for tetrahedra. It should work for tetrahedra. The shape. So for tetrahedra, the shape of this, so this parabola you saw in my plots, it will be replaced by something like 5/3, I think. So it's a different power law. And yeah, I was in an email exchange with them, so they're pretty surprised that I was able to predict these 5/3 from the shock waves. Right, and yeah, and so from Jean Dalibar's perspective, it is all somewhat a consequence of the scale invariance, of the fact that two-dimensional Gross-Pitaevskii doesn't have coupling constant in the two-dimensional Gross-Pitaevskii equation, has the same units as h bar square over m. Thus, it doesn't introduce a new length scale, and many things follow from that. And to some extent, it is, but one needs to. I need to be. I need to think more to just to show that this phenomenon is related to the scale invariance. I mean, it's not entirely obvious that this is right.
Thank you.
Any further questions? Okay, then let's thank Maxim again for the talk.
Thank
Thank
you.
you. It's yeah, it's nice to be back. So next time, at least in this fashion. Thank you so much. Thank you.
Next
Hopefully
time
in the
will be
not too distant future, we
Right.
can have you back in the office.
Thank you. Yes, with pizza. Right. Thanks. Bye.
Bye now.